Welcome everyone. Thank you for coming to this second part of the OAK tutorial series. So I hope some of you managed to, if you weren't already at the first one, if you had some time to just look over the slides or even to kind of try some of the command line examples yourself, just to kind of basically kind of familiarize yourself. So in contrast to the first session, which was more about using the command line to use OAK, today we're going to be, this is more focused on Python developers who want to use OAK in building kind of various kinds of applications. So what we're going to be doing is just going through essentially a Jupyter notebook. And if you like, you can kind of follow along with this at home. If you are not a Python developer, hopefully you're welcome to stay, and hopefully you can get something out of this. The good news is now with ChatGPT, and I'm not speaking facetiously here, anyone can be a programmer. You just kind of like type in what it is you're interested in doing into ChatGPT, and it will often give you, a working program that hopefully won't kind of infect your computer with a virus or anything like that. So it's becoming easier and easier to do tasks programmatically. But just to emphasize, OAK does have a powerful command line interface. And for many tasks, if you're not a programmer, that will be your first port of call for doing various kinds of applications. So the tutorial today makes use of a notebook that is already in the OAK repo. If you can either just kind of like follow along and watch, but if you want to try it yourself, there's various ways to do this. The easiest way is if you clone the OAK repo itself. Now, of course, normally if you want to use OAK, you don't need to clone the repo. It's available as a py package. You can just pip install it and use it. But just for today, it's going to be easier if you do want to follow along to clone the repo yourself. And let me just kind of like show you how that might work. So okay, I'm just going to do this. Make this a bit bigger so you can read it. Do a git clone. Oh, I failed to copy that URL. Hit the copy button, git clone. I still use the SSH method of using git. I guess maybe use HTTP. And then if you then change into this, it's not a bad idea. If you are a developer, you learn how to do this anyway, because you may want to contribute to the OAK code base at some point, and then you will want to clone it. Like all projects in Monarch, it makes use of poetry. And again, just to emphasize, you don't have to use poetry. If you want to use OAK programmatically, you can add it to your requirements.txt or whatever. But for if you are a developer within the Monarch project, then you will be using poetry. And so you can just do a kind of poetry install from here. But once you've done that, the developer environment for OAK includes Jupyter, so you can do and I'm assuming you're all roughly kind of familiar with Jupyter. There's actually quite a number of different notebooks in here if you check out the repo, but the one we're doing today is the developer's tutorial. And everything is set up so that this should just work. It does make use of a couple of local files, but again, if you've cloned the repo, everything will be in your path and ready to use. So now, before diving in to the tutorial, I'm just going to give you a kind of quick tour of the documentation. The goal here is not to actually read the documentation together, but it's to teach you how to read the documentation, but also to get feedback from you on how we can best improve this documentation. Because in building Oak, we're faced with a challenge. We're trying to, this is a general purpose ontology library. It's not just developed for Monarch. It's for use across not just all the obo ontologies, but any other ontology out there, as well as ontology-like artifacts like schema.org and so on. So it's quite broad and ambitious in the kind of user base it intends to tackle. And it's designed for quite a large variety of number of different tasks as well, ranging from kind of like data science, machine learning, to text mining, to just basically helping you build a kind of ETL pipeline that makes use of ontologies to build a data portal, that kind of thing as well as providing kind of like things like utilities for kind of curators who are working on ontologies. So there's a lot there. So there's no one correct path through the Oak documentation. So what we try and do is just try and give some general grounding where we can. There is a kind of tutorial here that you can try. It's not as complete as we'd like, but the first part here gives you a good grounding, the concepts in the command line. What we're working on here is a deeper dive into some of the kind of concepts and design decisions in Oak. And so if you are part of either Monarch or Obo, I really recommend kind of like just setting aside some time to kind of look through some of these. This is not the best place to start if you want to just quickly know, how do I parse this obo file? If you want to do something like that, then you're better off looking at some of the example notebooks or the tutorial. But this intends to be read when you've got a bit more breathing space and you can understand a bit more, you want to understand a bit more about some of the underlying concepts. But then if you are a developer, maybe the best place to start is actually just the package documentation here. So, and probably the best place is having a look at all of the Sphinx API documentation for all of the different interfaces. So most of the time you're going to be in this basic ontology interface here that has a lot of kind of like simple methods for being able to do things like get labels for ontology terms. Now, one thing that's quite new that may not have been here the last time you used Oak is we've been trying to do a better job, and we should be doing this across all of our projects, by the way, in putting executable testable code as doc strings within the API documentation. And you'll see if you mouse over any piece of code like this here, you'll see, oh, there's a little copy button. I'm going to take that and I'm going to copy it. And then you can go and you can kind of like go into, you don't even have to be using Jupyter. You can just do, you can just have a little kind of REPL running and say, and then you paste. And Sphinx is smart. It will, notice when I did the copy here, it's not copying these little chevron lines or the intended output. It's only copying the code itself. Oh wait, did I do a poetry install? Did I know? Yes, I did. I may have been messing with something just before we got this started. So let's just pretend we didn't see that. And we're going to go over into the other little environment I had running here. Meanwhile, if anyone noticed me doing something strange or wrong there, because I'm completely perplexed why that didn't work over in that other shell, I would appreciate if someone could help me, maybe debug that on the fly.
Chris,
but
could I make
yeah,
a request? So
sure.
some of the terminology you use in the API is surprising, like get adapter, and it's returning a term label. So if you could explain the function names, that would be helpful.
Absolutely. So yeah, so just to be clear, adapter isn't returning any label. So an adapter returns essentially a handle. So the analogy here is if you're a Java developer, you've worked with JDBC, you know, if you're a Python developer, you've worked with SQL Alchemy. Yeah. The first thing you do when talking to some database engine is you get some kind of like handle / adapter / connector. It's following the kind of like the the kind of like the engine design pattern here. So what this is doing, well, this is just importing the method. Then this is like I'm saying, okay, get me an adapter that will help read this file here. Then once I've got the adapter can has just methods like get me label. So we used to have more descriptive Java-like names for some of these, like get label from query and things like that. But we switched to this kind of like more compact form. But we don't have a 1.0 release yet. There's issues on the repo for this. Really, I would, Oak should be driven by all of you, and we want to have method names that are intuitive and as clear as possible. And now is a good time to go in and kind of like put in your thoughts about what would be better method names if we need them and so on. So yeah, so what this is essentially saying is you're asking the adapter for a label for this this Go ID. All right. We're going to kind of like hop over to the notebook now. But yeah, just again to emphasize, all of these should be copyable. They should all kind of like work in a REPL as well. But we're going to switch from the REPL to the notebook here because it just makes it a little bit easier to see what's going on. So I'm going to kind of like just do a restart of this one, just so everything is kind of like fresh from scratch. So there's a little bit of an intro here. If you are running things locally, we're going to run this first cell that just kind of like puts the notebook in a state such that it's at the top of the repo. This means that our little example files that come distributed with Oak, that again, you don't normally need if you're building an application, but if you're just want to run the tests and so on, you can run this here. And oh, I didn't hit run. Okay, so run. Okay, there I am in the there we go. I don't know why I didn't show anything the first time around. All right, so again, this just recapitulates what we just said here about being able to copy the documentation. You can kind of like take that same example, run it in a notebook here. And there we go. This Go ID here, when we look it up, it's and get the label for that ID is indeed nucleus. All right, so now most of the examples we're going to be going through here makes use of the SQLite backends. You can tell this because if we were accessing it as a file, it'll have .db at the end, which is standard for SQLite. I'll show you in a moment another way to be able to download a ready-made SQLite database. But just to let you know that Oak does have ways of accessing other kinds of ontology distributions. It can use obo files, it can use obo graphs JSON files, it can, albeit very slowly, parse owl and turtle files. So just to kind of like prove to you that is the case, we're going to try getting a separate adapter here. And this adapter is behind the scenes, happens to be using a library called Pronto to read this obo file, but you don't need to know that because regardless of what the actual underlying adapter is, they should largely conform to the same interface and give you the same results. So again, this is just if you've used something like JDBC, the same idea that it doesn't really matter what kind of database backend you're talking to. If they all conform to the same interface, then you should get the same results. Yeah, modulo some interface, some adapters may not have the ability to be able to do certain kinds of things. And the last tutorial, we talked about how you could use bioportal backends and how we could use Ubergraph backends. We're not going to do any of that today. We're going to focus just on using the SQLite backend, and in particular, we're going to use these ready-made SQLite versions of different obo ontologies. And you can tell these because when we call the getAdapter method, we always use this syntax here. And so this is telling us use the SQLite back. Oh, double clicked on that. Use the SQLite backend. Use it to pull something from the obo library with this ID. So this is the syntax used to get the SAL ontology, for example. And so just to prove that works, getAdapter, pass in the selector syntax for the SAL ontology, and say, okay, get me the label for this ID, which is neuron. Excellent. Okay, so we can move on and look at some of the other functionality provided in the basic ontology interface. So, again, it helps to have kind of like covered some of the concepts in the first part of the tutorial here, especially if you're coming from an OWL background, because the way Oak thinks about ontologies and ontology graphs may be slightly different from how you think about things if you're used to working with something like Protege, or you use browsers like Ontobe, which only show you ISA hierarchies. Oak has a richer notion of ontology graphs where, just like in the kind of like the classic gene ontology paper, we think of the graph as including other kinds of edges like ISA and part of edges. But just for now, we're going to restrict things to the ISA graph. And we're going to ask Oak to give us all the ISA ancestors of this concept here, which is the concept for a neuron. So we're going to use something called the Oak vocabulary module here. And the idea with the vocabulary module, it just gives us constants or static variables that refer to kind of commonly used predicates, such as the RDFS subclass of predicate. So so here we're saying get all ancestors of this, but all methods such as graph methods such as ancestors are typically parameterized by this predicates parameter as well. So we're just going to loop through each one of these. We're going to print the ancestor, but we're also going to get the label for that ancestor as well. And there we go. One thing you will notice is that the ancestors does have things that are not in the SAL ontology itself. And this is because, like many ontologies, the SAL ontology is bundled with bits of other ontologies too. And we'll see how that can be useful in some of the subsequent methods following on from here. By the way, I see some chat in the, I can see that there are messages in the chat window, but I'm not going to go and look at them unless I'm directed to, but please feel free to kind of like interrupt if you have any questions as we go along. All right, so you can do the same thing with descendants, but this time I'm going to try something that actually turns out, to be wrong here, and we're going to explore why it's wrong. So here's the code here. I'm going to say, okay, ancestors, that's fine. Let's say I actually want all the descendants. There is a descendants of neuron, that's to say all the subtypes of neuron in the SAL ontology, of which there may be quite a lot. So I may actually want to get this list of neurons and then show the length of that list here. But it turns out that that will throw an exception. I wrap this in a try except just because we're in a Jupyter notebook here and we want the notebook to be able to run from beginning to end without issues. But if you do try and do this, you'll get this kind of like strange Python message: objective type generator has no len. So what does that mean? And the basic idea here is that Oak generally will not return lists for you to consume. And the reason for that is that can be highly inefficient in certain kinds of scenarios, especially if your adapter is talking to some kind of like remote database backend, and it will with us to use some kind of like API with chunking and so on. And it also, prevents you from writing things in a more kind of streaming fashion within your own code. So typically we make use of iterators whenever Oak needs to return some kind of list. And so if you're not familiar with the concept of iterators, there's lots of great documentation online you can read. There's a little bit about it in the Oak guide here, but just for the purposes of this tutorial, we're not going to go too much into that, and we're just going to wrap things in a list call here, so that we don't have to think too much about it. And so if you call list on a generator, it will basically kind of like iterate through all of the members of that and turn it into a list. So if we do this, then it will indeed work, and it's a normal Python list. We can get the length of it, 454. And you can also use other Python collection constructs as well. So in this one, we are we're going to import another relationship type here, part of. We're going to do a query here to get all of the different parts of the forebrain. So this is the Uberon ID for forebrain here. This gets us all the parts of the forebrain. We can see that there's 219 of these. Just a little segue here. If you're wondering, wait, what are these Uberon terms doing in the cell ontology? And again, it's because many obo ontologies will bundle bits of other ontologies with them. And in fact, you can think of these ontologies as little mini knowledge graphs. They've actually got kind of quite rich relationship types, interconnecting concepts. So the cell ontology will have edges connecting to Uberon, to Go, and so on. And you can read more about this general strategy in the obo-academy documentation. But just for now, all we're going to do is we're going to do a simple Python set intersection between parts of the forebrain and neurons, and then just iterate through these and list them. And then we can see these are all the cell types in the cell ontology that are both neurons and are part of the forebrain. This is probably an undercount of the true number of cell types there. And in fact, I just realized I didn't use the cell ontology in the best way here. I should have used the soma part of relationship, but that's a bit of a distraction for what we're doing today. But this is kind of good enough for our purposes at the moment. And if you're familiar with doing things in
there's a
Protege,
question by Peter. One moment.
Oh yeah, go for it. Mm-hmm.
Peter, do you want to ask us yourself?
Yeah, I'll read it out. It's fine.
How do we know that all Uberon terms were imported into the
Right.
cell ontology adapter, though?
We could query that, but as those of us who are obo people here will know, that we just know ahead of time that in fact all of Uberon is not included with the cell ontology release. What we do is we run a robot. Most ontology pipelines that use ODK to make the releases will do this. They will use a robot extract that will essentially, more or less, follow the graph out from all cell ontology concepts up to their parent, their part of, and soma part of Uberon concepts, and then follow up the graph. So it's deliberately only a subset of those. Now, if you do want to make a knowledge graph that is all of CL and all of Uberon and maybe all of HPO and things like that, there are a few different things you could do. There are some ready-made products in obo and in the semantic SQL registry. For example, the Finio ontology that Harry Caulfield makes is essentially a union of all of the different ontologies that we care about in the Monarch universe. So it's got all of HPO, all the phenotype ontologies, all of Uberon, all CL, and so for doing a lot of kinds of operations, it's quite useful to use that. But today we're just like looking at the cell ontology here and the limited subset of Uberon that it brings in. All right. So again, neurons part of the forebrain. If you're familiar with using Protege, you can think of this as being similar to a DL query that you can just type in Protege, which is neuron and part of some forebrain. In theory, the DL query is more complete. In practice, with the pre-reasoned versions of ontologies that get released, you will essentially get the same results here. But again, just to help you kind of like connect this more graphy way of thinking about the universe that Oak exposes with our kind of like what you may be familiar with Protege, you can think of this as the bridge here. All right, so these methods just return the actual terms themselves. What if we want to query for the actual relationship triples themselves? So there is a method called relationships here. This takes as input. Well, actually, this is a good time to pop on over to the documentation here. Here's the basic ontology interface. I wish there was a way to get a little index on this side, but let's just do a kind of query in here for the relationships method. And again, there's a little chunk of code that you can copy and run if you want to, that runs over the little test ontology that we distribute here. You can see this takes a lot of different parameters. Usually in Oak, the most important ones are first, and ones that are kind of like have sensible defaults come later. So 99% of the time, you don't need to worry about a lot of these. And mostly you're just going to be constraining things by subjects, predicates, and objects. If you're familiar with the RDF-lib API, this is not so different here. But one difference, if you are familiar with that universe, one difference that's worth emphasizing is this doesn't just query triples. This queries edges in the relation graph sense. So anyway, so this takes subjects, predicates, and objects. Again, if you're familiar with Python, you'll know that methods can take both positional arguments and kind of like by arguments. Wait, is that right terminology? I think you know what I mean. But the first argument here is kind of subject. So if we wanted to, we could be explicit if we want to and do this, but it will work in exactly the same way. But equally, if we want to be lazy, we just know that the subject's argument is first here, gives us exactly the same results. So what this is doing is just querying all direct relationships that emanate from, i.e. where the subject is CL540. And so you can see you can get not just the is edges, but you also get kind of things like this as well, which you may say, okay, what's that? Well, we'll get to what that relationship is in a moment as well. We can also kind of like feed in, you can use a Python print string to give us more information, maybe on the label or for the object here as well. You can see, okay, yes, it's a subclass of neural cell and electrically responsive and electrically signaling cell. Yeah, personally, I think, CL is overloading is a little bit here. You wouldn't normally expect to see so many is, but and this is actually reflecting some nuanced release issue here with CL. Normally you wouldn't expect to see a buffo class that high up. Cell ontology developers on this call, let's take a look at that. But we can also do this as well. Let's get the label for the predicate as well, just to kind of see, okay, this is the capable of relationships. So a neuron is capable of transmission of nerve impulse. That seems reasonable. And what does this one do? Oh yeah, so this is just, we can also do the query in the inverse relationship. So here, neuron is in the subject's position. Here we're going to say, we're going to do a query with it in the object's position. That is to say, find all relationships that connect to neuron. You can see interneuron, polymodal neuron, multipolar neuron. These are all subclasses of neuron. Now, what we can do that is quite powerful as well is that we can query for the entailed relationships, the inferred relationships. Behind the scenes, what this is doing is it's making use of a ready-made relation graph table. And if you've not already seen the previous obo-academy tutorial on ubergraph and relation graph, I think we did one. I definitely recommend watching that one. But the basic idea here is that this is not just direct relationships, but it's it's all the valid results from the transitive closure as well. And you can see if we ask for this, what kinds of things is a neuron part of? It's part of a nervous system, but you also get back all of these kind of like trivial edges as well. This is to be expected. You know, you wouldn't normally present this to a user, but this can be very useful for kind of querying purposes. And so you can do this in the opposite direction as well. So just to prove that that works, let's maybe do let's maybe get all of the ISA children. Actually, we're going to do this this is probably going to explode quite a lot. So what I'm going to do is I'm just going to wrap this in a list and maybe just get the first 10 of these. Oh, and this time we're actually interested in the subject. So is this making sense? Please just interrupt me at any time if any of this is kind of like confusing, or if you need not clear on the terminology and so on. So yeah, this is the first 10 is a children of neuron. Well, I'm going to move this down just so that that piece of text stays with that. All right. So the nice thing about working with notebooks is it's very easy to intersperse data science tools like pandas data frames and so on. So this is just to demonstrate how to do this. Let's import pandas. We're going to get our forebrain neurons again. And for all of the forebrain neurons, we're going to make a little table essentially where we put the triples and their labels in here as well. So we do that and we get the data frame, and there you go. And so Jupyter does a fairly nice job of rendering these data frames. And if you like Panda syntax, you could even do something like get all of the relationship types in the cell ontology and do various kind of like pandas data framesy type operations on this. All right, so we'll come back to pandas in a moment, but for now, let's carry on. Just look at some other really basic kind of like functionality. So you can get a list of all aliases for neuron, nerve cell, and neuron. Now, if you're familiar with obo, you might be saying, "Oh, hold on, cell ontology has much richer information about synonyms. I want more than just the strings." And we'll get to that, but the basic idea here is that Oak provides kind of simple methods for doing the most common simple operations, and then kind of gradually layers in more more complex operations that allow you to get to some of the rich granularity that we have in some of these. So part of this granularity is that we actually have typed predicates, or what Obo calls synonym scopes for these. So we can actually ask for alias relationships, which will return essentially simple tuples of the predicate and the alias. And so you can do that. We can say, oh, okay, so well, we get back the label itself, which is considered a kind of reflexive alias. We also get the predicates like obo-anal, has exact synonym nerve cell. And again, just to emphasize, Oak is meant to work over not just a small subset of ontologies in obo, but all of obo. And one of the challenges is people use different predicates for aliases in obo, and Oak should do a good job of using all of the different predicates that people use in the wild, and it even has facilities for kind of like providing a mapping file so that you can work with kind of things that are even further outside the obo universe. But again, just for 99% of the cases that we care about, the plain standard methods should work just fine. There are other methods for being able to do things like retrieve provenance for synonyms. Sometimes synonyms have PubMed IDs. You can do that. We're not going to get to that today, though. In a similar vein, we have some quite simple methods for retrieving the mappings for a term. So this method here, actually, let's just do it like this. We can do, this looks a little nicer. too many parentheses. We can do things like this. Again, this is just using the basic ontology interface that has a very kind of like simplistic, deliberately simplistic view of ontologies, and its view of a mapping is basically a mapping is a tuple of a predicate and then the kind of external ontology term. Now we'll get to kind of like ways to get at the richer SSSOM model later on, but for now we're just sticking with the basic ontology interface. So another thing that's considered basic is this idea of subsets. We're going to switch to the to Go here. That makes use of those. I think probably the most kind of like detailed kind of like subset coverage in the obo ontologies, and they're often, just to align you with terminology, they're often called SLIMs in the Go universe. So here we're going to get a different adapter. We're going to get a Go adapter, passing in this syntax here. Let's get all of the different synonyms used here. And again, this is not actually a Go, sorry, this is synonym subset. This is not actually a Go subset here. This is from Kebi. Again, it's because we're pulling in, this is Go Plus essentially, that pulls in parts of Kebi and so on. But what we're going to do now is we're going to try the subset members method. This will get all the members of a subset. So we're going to ask for all members of just GoSlim generic. Here's the members here. That's all very nice. But again, you know, another nice thing about Jupyter Notebooks is that you can use libraries like Matplotlib and Seaborn to kind of like plot things. So here's some kind of, I'm not going to go over this code itself. And these days you can just get ChatGPT to write code like this for you. You don't really need to, you know, if you're not kind of like a pandas geek, you don't necessarily need to know this in detail. This is just to demonstrate it's really easy to do on the fly quick analyses where it's like, oh, I wonder how related all of the different Go Slims are to one another. Let's just kind of like plot this in a heat map with some dendrograms on the side, so you can see that, oh yeah, the generic Slim is quite similar to the prokaryote subset and so on. Yeah, that's all very nice if you want to analyze Slims. It's just to demonstrate the easiness of this. So let's quickly go over a few other methods. We're going to switch to a different interface now. This is the search interface. It goes beyond what you can do in the basic ontology interface. This is for essentially doing lexical searches over ontologies. The adapter that we're using also supports the search interface, so we can use any of the methods here in search interface as well. So we're just going to be doing something called like a basic search. By default, basic search does a label lookup, so we're essentially just looking up an ID by its label. What happens if we try this with, you know, a capital M N neuron? We don't get any results. That's by design, just because we want this to be kind of like fast and deterministic. So by default, it's case insensitive, but we can make use of the search data model, and you can actually pass in a configuration object that determines how the search is meant to operate. So all of the OAK data models are kind of documented. They've got their own W3ID URI, and so you can see here how we can specify a search configuration, what all the different fields are that you can place on a search configuration. I won't go into this in detail, but I'll just kind of show some examples. The most basic thing you can do is create a configuration that will force your search to be case insensitive. We now parameterize our search query with this configuration object. Then you'll see that we do in fact get results for capital N neuron or any kind of like regular variant of that. You can also do kind of like starts with type queries. So you can see, find me anything that starts with the string neuron, and you get back I think There we go. It ran those out of order. So here we get all of the different strings that start with neurons. You can also do regular expressions as well for anything. Yeah, this is essentially the same idea, but we're passing in a regular expression. The caveat here is that if you are using the SQLite backend, it can, at the moment, it can only handle the subset of regular expressions that can be translated into SQLite, SQL-like queries. This limitation may be kind of like lifted later on. There's ways to build full text indexes in SQLite, but right now we're just using the very basic SQLite functionality. You can also do search on other properties like the xref property or kind of Scotch properties. Here we're going to do a search. We're going to be searching over the mapped identifier field. I'm going to say find me all nodes in the cell ontology that are mapped to this FMA concept here. You see there's actually 2 of them. It's maybe surprising. We might expect these to be one-to-one mappings, but that's something for the cell ontology group, some of whom on the call to take a look at. Okay, so this takes us into mappings. There's also a more powerful mapping provider interface here that will give you full access to the SSSOM data model here. So there's an example here, but we're going to use one of the already made cell ontology examples here. What we're going to do now is we're going to say, do a bit more of a kind of complex pipeline here. We're going to get all of the different neurons in the cell ontology. Again, this is just getting all the ISA descendants of neuron. Then we're going to get mappings for all of those neuron terms. So you can pass in a list of entities here to the SSOM mappings method. And so let's run that and we'll see we do indeed get 186 different mappings here. Let's just do a raw a raw print of the first element of this list. And you can see it's maybe a slightly ugly looking mapping object where most of the fields in SSOM are blank. So let's get a nicer kind of like YAML representation of this. We can do this using the linkml dumper, and let's just do for the first 2 of these mappings, let's just dump them in YAML, and we can see we're not really making full use of the SSOM model here. This is not a limitation of oak per se. It's just right now the way we bundle mappings in ontologies is such that we only include pretty minimal metadata. We're also using this slightly ugly hasdbxref rather than a SCOS mapping. This will likely change in future, and we're likely going to start distributing richer mappings with SSSOM metadata alongside our ontologies. But until that day, you just get this fairly minimal set of minimal kind of objects conforming to SSOM. So I won't go into all of the other interfaces, but just very quickly, you can do things like text annotation as well. You can, I'm demonstrating this again just on the cell ontology. If you want to do text annotation, you might also want to look at using something like the bioportal backend adapter that will give you kind of like mappings over like a very, very wide range of different ontologies, which can be kind of like useful for, just kind of like, trying to get a handle on what kind of ontologies are best used to annotate some text. There's also various kind of like plugins for Oak that can use machine learning frameworks like SciSpacey as well. Personally, I think traditional named entity recognition is going to go away as we use methods like spires that kind of like take into account looking at the broader semantics of the sentence. But just for now, if you just want to do basically extract kind of like little strings like kind of intestinal epithelium from Uberon matches this span here, this works reasonably well just using the default method. So just quickly, let's go into the graph interface as well here. The obo-graph interface can be used with any backend, but it provides obo-graph abstractions over your ontology. So you can do things like get me the ancestor graph of a whole bunch of CL concepts, in this case just neuron, following up the path walking up the is it and part of relationships. So we can do, boom, okay, let's, we've got a graph object that conforms to the obo-graphs data model. We can say how many nodes have how many edges, okay, as expected. You can do things like export this into GraphViz as well. If you do this using the bare bones arguments, you get a kind of very plain gray looking graph, but you can also pass in a style sheet here as well. You can just plug in your own style sheet, or you can just use the default style sheet that will give you different colors for different ontologies. It will kind of like highlight your focus term in bold. It will use these little kind of like symbols, which I gather may not quite work on Windows. I don't know if we fixed that. But you can kind of like plug in your own ones there if you like. All right, so there's various other interfaces I didn't show you for doing other kinds of operations. Most of those interfaces work with just the ontology in isolation. Now, working with ontologies in isolation is great if you're an ontologist and you just want to analyze an ontology and so on. But typically when you're working with an ontology, you want to be working with related data as well. This data is usually distributed in the form of what we loosely call annotations. Now, annotation is one of those fuzzy words that means lots of different things in different contexts. And every ontology's notion of an annotation is maybe a little bit different. An HPO annotation is very different from a Go annotation, and it's very different from a gene expression annotation you may get using Uberon from BG, but there's certain things that are in common to all of them. So Oak, it's at the moment, it doesn't have full functionality for working with everyone's different annotation formats because there are so many of those. For doing things like that, that's where Monarch and the Monarch knowledge graph come into. And there's a bit of a kind of fuzzy line between these. But and Oak is really designed to work in concert with however you're working with your annotation files at the moment. But just to sort of demonstrate some of the power that you get here, there is a kind of a small simple annotation or association object model within Oak that exposes associations essentially as simple triples, as simple kind of predicate object triples. And just with that simple simplification, you can still do quite a lot of useful operations such as term enrichment. So let's get into it. Let's get into kind of like working with annotations. This time we're going to use, now hopefully I'm not overloading you with too many concepts here. A lot of the time, again, if you're just working with ontologies, you don't need to do this. But sometimes you want to work with some kind of combination of ontologies and annotations. The Oak configuration library actually gives you some ready-made combinations that are useful. So this is the human phenotype ontology plus the G2P annotations that are distributed as part of HPO. So we can ask for this adapter, and here we're passing in essentially a kind of a specification of what these are, and we'll get to that if we've got time. We can say, okay, then show me a list of all of these kind of associations here. While we're doing that, maybe we can take just a brief look at what that spec looks like. So it's quite simple. So it's basically you can kind of like you can think of this somewhat similar to an OWL imports. We're basically saying, okay, bundle in this one ontology HPO with this this kind of like this set of association files as well. And you can put as many ontologies and associations here as you like, but a common pattern is just of like one ontology with one set of annotations. Okay, good. So we got quite a lot of different annotations there. Let's just query the kind of like first 15 of these. This is a little bit slow the first time it runs, just while it caches these. And you can see, again, we are intentionally, we don't try and encompass the full richness of everyone's annotation model here. We're just trying to get the basic information. What is the main entity being associated with the main term? So this is NCBI gene IDs. associated with terms. So let's so this shows how you can do queries over these annotations. So we're going to get all annotations where the object is this HPO term, sensory ataxia, and we're going to also include a closure query where we're going to also get anything that's annotated to and is a descendant of this. This is a parameter you will want to vary depending on what your annotation set is. If you're querying BG annotations for Uberon terms, you're definitely going to want to include part of in there as well. You may want to try, other relationships like develops from, but I'd be very careful there. But this, this kind of gives you the power to kind of like choose over how you're going to propagate over your ontology of choice. And so we get 15 different associations here, and then we then.
Can I interject for a moment, Chris?
Yes. Mm-hmm.
This is super awesome. Like I didn't realize that you've done or that this was implemented. But what exactly are the steps involved for, like, let's say someone else's annotation files to be added to the core config here? Is it like building a sort of little ETL script? What is involved? Let's say Flybase wants to add their annotations somewhere.
Yeah. So Pombase have already. I don't know if Kim is on this call. Kim figured out for Pombase pretty quickly. So you can just write, you can do it one of two ways. You could just write, all right, well, let's quickly, so we may end up overrunning here, but I think it's fine. You could do something just like this, where you do something really simple. So I've got to move my bar out of the way, do something really simple and dumb, and you just kind of override the parse method. You take complete control of yourself, use Python dict reader, which I'm sure if you're a Python developer, you're familiar with, and then you just kind of like create association objects and yield them. Some association formats, and this is, sorry, our fault in Go, are a little bit trickier because they don't have this kind of positional headers. So there's kind of like little, there's little kind of like patterns that you can use here. So let's, and so you can do it in a kind of lazy way if you like, where you can just say, the subject is kind of column 0 and the object is column 3. So you can do it that way, or you can do it this way if you like. But this, this part is, we need to think, without those of us in Monarch, kind of like think of our best strategy here as well, because there's a lot of work that can be leveraged in COSA as well for normalizing all of these many different ways people do kind of association files. And so there's a bit of overlap there that we should kind of think about how best to do this moving forward. But the goal within Oak is just to kind of expose the simple part so that you can do kind of common operations like gene set enrichment and so on. All right,
thank you.
So yep, so we've got 15 genes. Just to prove to you that they exist, here's 5 of them. What we're going to do now is we're going to use a different adapter, the translator adapter, that only implements some mappings and normalization. And we're going to use this to normalize all of these gene IDs into Unipro IDs. Then what we're going to do is we're going to get the Go specification here, in particular the Go human one. And the reason I map these to Unipro is because Go natively uses Unipro for human. And then we can, once we've done that, we can then go through. This takes a moment or so to download, but I can talk through what this is going to do. We're going to basically call this enriched classes interface here. This is part of the class enrichment interface. So we can quickly look, class enrichment calculation interface. And so this kind of provides a method here again with a kind of like standalone example that will run. You can pass in all of these different parameters. And again, the most important ones are first. So you pass in essentially the list of genes that you want to test for enrichment. We recommend that you always specify a background set for enrichment. And then everything else you can probably pretty much stick to the to the defaults there. And it's still running, but just while it's running. Oh yeah, there we go. So we get these are the results we get. So again, remember our initial HPO query was for sensory ataxia, and the top result there is not unsurprisingly go myelination. So this is just a nice little confirmatory analysis. And then we can kind of like keep on, we can do things like kind of like plot the results of the enrichment analysis in a graph, as can be shown here. And I was going to show you how to do term enrichment using OntoGPT, but we don't have time, so that will have to wait for another time. And instead, I'll just stop here at the end of this notebook and take any quick questions from there.
This is awesome. I just want to summarize real quick in the chat. We have tried the codes, and for none of us there was a problem. So there must have been some specific issue in the first, this first thing that you showed.
Okay, good. I'm hard to hear that. Yeah.
And any other questions? Right. Now, this was very comprehensive, a lot of things to digest, and a great video resource, I think, that we will circulate to all of our developers. So thanks a lot for taking the time to do this, and awesome features on the annotation parts. I think this will take a lot of pain away from what I needed to do in the next weeks. So thanks a lot, and yeah.
Very good. Thank you all. Yep. And please, any feedback is really, really, really useful. So.